afternoon to everybody, and thanks for coming. My name is Mike Kay. I'm the Market Development Manager from Lumen Dynamics, and we make the Uncured style UV systems. And I'm going to talk to you today a little bit about high throughput, low temperature UV assembly. And we're going to talk specifically about a couple of different technologies available using either LED or arc lamp technology. Just to give you a little bit of a background on Lumen Dynamics, as a company, we've actually been around since about 1984 with a couple of name changes. We started as EFOS, we became Expo in 2001, and then just back in October of 2010, we were purchased by Riverside Company and are now the Lumen Dynamics Company. We do have offices globally, and at this point there are about 15,000 of our UV spot curing systems in use worldwide. We sell both lamp and LED technologies, so what I'll be talking to you today about is some of the advantages of each technology and really try to help you decide which technology may be best suited for your application. Some of our typical applications within medical include things like catheters, syringes, and also in electronics, things like cell phone cameras, displays, are all different things that are currently using UV spot curing system in assembly. Just to give you some information on the different systems we have available, our lamp-based system, an Omnicure S2000. This system uses a 200-watt lamp. It includes a dichroic reflector, which helps to eliminate the infrared energy, and that's very important in minimizing the heat in your UV curing process. It has a typical lamp lifetime of about 3,000 hours. You can adjust the irradiance on the system. And one of the things that we have in our spot curing systems, it's somewhat unique technology, is something called closed loop feedback, where we're able to monitor the output of the lamp. And as the lamp ages, it will degrade in output, and we can automatically monitor and compensate for the degradation so that it has a very repeatable output for the lifetime of the lamp. And that's a unique technology that we have at Omnicure. It's also very automation friendly, and we have some filter selections available that allow you to tailor the wavelengths of light specific for your application. As far as LED systems go, we have the LX400 Plus LED system. Now, as an LED technology, you get a much longer lamp life, about 20,000 hours, a peak irradiance of about 9.5 watts per square centimeter. That is for a fairly small 2mm spot. The system's available in 3 different wavelengths. There's 365 nanometers, 385 and 400 nanometers. So you can select the wavelength that matches up best to the adhesive that you're using. And we also provide specific lenses for each of the LED heads, which again allows you to optimize the working distance and spot size specific for your application. And one of the things we've just introduced is a new LED light meter, which is designed specifically to measure the output from an LED system, and it's a NIST traceable meter that we just recently launched. The other LED product that we have available is what's called an LED light line. So in this case, instead of a spot of light, it's actually a 3-inch wide beam of light. Again, you have a lifetime of about 20,000 hours. It is the same wavelength, or it's got 365 nanometers, 400 nanometers available. The benefit of LED being such a narrow wavelength is that you get very minimal heating in your UV system. So you don't have any excess wavelengths being absorbed by the parts or other parts of the adhesive. So you have very low temperature curing with LED. In this case, it also provides quite a nice peak irradiance. This particular line gives about 2 watts per square centimeter in peak irradiance, and is really an ideal one for small parts that are being moved along on a conveyor type system where you can cure in an automation assembly type environment. Just to give a bit of insight into the market, LED is really the new technology that's coming along. There's a lot of interest in people deciding whether or not it's appropriate for their applications. At this point, we see globally about 60% of the UV systems are still using lamp-based technology. About 40% have switched to LED. A lot of that depends upon the specific applications that you're in. A lot of the electronics applications have adopted LED quicker than things like medical device, which is a bit more difficult to switch your technologies, and so therefore the adoption has been a bit slower. But you can see that there is definitely growth within the LED, but the lamp-based systems still have a very significant portion of the UV curing market, and in a lot of cases may be the better technology solution for your application. So what we'll go through is some of the different factors that people will typically look at when deciding on what type of technology for their UV curing process, and see where there's benefit in either lamp or LED-based technology. So the first thing we'll take a look at is lamp life. So as I mentioned, a lamp system, typically you get about 3,000 hours lifetime out of a lamp, which is pretty good. You do get degradation, so that at the 3,000 hours, you have about half of the initial energy left. But if you look at an LED system, you can get up to 20,000 hours of lifetime. One thing to note, though, there is still degradation within the LED, and one of the things we commonly hear from customers is that LEDs have no degradation over time, which is not the case. So there still needs to be some compensation made within your process, as the LEDs will degrade over time, and certainly the degradation depends upon a number of different factors, the most important being how you control the temperature of your LEDs during its lifetime. So in this case, certainly you get better lamp life from an LED system. The other thing LED does is it is considered more of a green technology as compared to the lamp systems. Now, UV curing in general is considered somewhat of a green technology because the UV adhesives are more environmentally friendly. They have a lower solvent content than many of the other adhesive technologies. And so LEDs are very compatible with that. They have no mercury within them. They require much less power to drive the LEDs, and they last longer without consumable items. So it's a more green and environmentally friendly technology. When we look at the different factors that will actually come into play when you're curing your adhesive, what we typically look at is the exposure time, the peak irradiance, the wavelengths that you're using, and heat. And heat is really a byproduct of the first three factors that you put into your process. And what we have found within our testing is that the way you control your irradiance, your time, and your wavelengths can have an effect on the physical properties of your final cured adhesive. So the same adhesive can result in a different bond strength, different flexibility if it's cured in different ways. So it's important that you understand how your adhesive is curing so that you can maintain a very repeatable process. So if we look at just peak irradiance or power in the light source, lamp has a significant advantage over LEDs. Here you can get about 30 watts per square centimeters peak irradiance from a lamp versus about 9.5 for an LED. You can also get much larger spot sizes, up to about a half-inch spot size using a lamp system versus an LED system. You're limited to about a 5mm spot. So there's certainly much more flexibility using a lamp system. The big difference, though, you'll see is when we look at the spectral content of an LED versus a lamp. You can see the lamp system is a very broadband system. You have wavelengths from 250 up to about 500 to 600 nanometers versus an LED, which is a very narrow spectrum. In this case, this is our 365 nanometer LED. So it's a very different spectrum of light between the two different technologies. So if we look at how the adhesive is curing, what a UV curable adhesive requires is a sufficient amount of light in the correct wavelength range in order to activate the photoinitiator. When you're using a broad spectrum such as a lamp, it's much easier for you to match the spectral content of the light to the absorption requirements of the photoinitiator. It's much more difficult when you're using a very narrow band light source such as an LED. So it really becomes critical that your LED wavelength matches the absorption range of your adhesive. And this is where people can run into issues where they try to replace a lamp process with an LED. If the LED doesn't match the spectral absorption of the photoinitiator, it doesn't matter how much power you put in, the adhesive is just not going to cure. So there's certainly a benefit for matching the content with a broadband spectrum. One of the other things that comes with a broad spectrum is that you get light outside of that is needed by the photoinitiator, which can be absorbed by the adhesive. It can also be absorbed by the materials, and that tends to generate heat. In certain conditions, heat can be of benefit. It can help to speed up the curing process, but many times heat is something you're trying to avoid, particularly using heat-sensitive parts. You're trying to cure at as low heat as possible. And the chart here shows that with using a lamp-based system, you can get up to about, for this particular application, about 50 degrees Celsius during your curing process. Now, you can use different spectral filters to eliminate some of the unwanted wavelengths and reduce some heat that way. However, the narrow LED is a clear winner here. In this case, there was barely any heat generated within the curing process, and that's certainly one of the clear advantages that LED technology brings to a curing process. As I mentioned, with our LED products, you have a choice of different wavelengths to choose from, and so the question becomes which one is going to be most effective. Certainly, most adhesives, if you look at the spec sheet, will specify 365 nanometers because most of the adhesives were designed to match up with that peak in the mercury bulbs. However, if you look, many of the free radical adhesives will cure very well with wavelengths up to about 420 nanometers versus some of the cationic adhesives where they tend to cut off a bit lower at 380 nanometers. So again, it really depends upon the specific chemistry of your adhesive for the wavelength selection that you're going to use. Some of the other things to consider are things like through cure, where a higher wavelength such as 400 nanometers will give you a better through cure. However, 365 shorter wavelengths tends to give you a better surface cure. So there's a number of different factors to consider when actually looking at the most effective wavelength to be used in your curing process. The other thing that needs to be considered is the substrate itself. And this is one of the things that some people don't consider when they look at their curing process. And this is one example where we had a customer who was using an adhesive that specified 365 nanometers, and they were curing between two pieces of polycarbonate. But what they found was, if we look at the absorption curve on the right, that at 365 nanometers, the material was actually absorbing about half the energy of the light. So when we tried it at 400 nanometers, now you were getting about 60% more light through the parts, and so you're actually getting a much more efficient curing. And what we found is even though the adhesive had specified 365 nanometers, we were able to cure faster at lower temperatures using 400 nanometers. So again, you need to take into account the actual parts that you will be curing when you're selecting your wavelength. The last thing to consider, particularly when moving from a lamp to an LED, is that many of the adhesives have been designed to be used with a broad spectrum, such as a lamp. They may have multiple photoinitiators with multiple absorption peaks. So what happens when you go from a broad spectrum to a very narrow band? Do you get the same effective curing with the narrow band light as you had with the broadband? So some of the tests we've done, and in this case, we used an indirect testing where we tested the micro hardness of adhesive. And we took a number of different commonly used adhesives. We took a lamp-based system and an LED-based system, and we tested them to compare. And what we saw was the micro hardness reading is very similar. It's actually a little bit better for the LED. And this would indicate that the adhesive samples are cured equally well with LED as they are with lamp. However, on one particular adhesive, when we went a little bit further and did some further analysis on the adhesive, where we actually ran it through a DSC system, where you can now actually see the amount of uncured material what this chart here shows is that in this particular sample, even though the indirect test showed that they looked like they were cured equally, the red line on the chart indicates that there was actually quite a bit of uncured material in the sample cured by LED. So even though it looked like they were being cured equal, they really were not. The lamp actually had given a more fully cured adhesive than the LED system had. And without doing this further analytical testing, you may not have known. So really, the moral is that until you actually do testing, curing with LED may not be the equivalent of your process that you're doing now when you're curing with lamp. And so it's really critical that you test to make sure that your current adhesive is compatible with LED. Finally, when looking at radiometry, again, a number of customers who have radiometers designed to measure broadband lamp-based systems try to use that for measuring their LED, and it doesn't work. The technology for LED radiometry is much different because you have a narrowband spectrum. The calibrations are different, and so you get much different readings if you're not using the correct radiometer. So we have a new LED radiometer that's designed to measure the specific wavelengths of the LEDs that you're using, versus many of the current radiometers which are designed to measure over a broad spectrum. And since you're not producing a broad spectrum with LED, you may get inaccurate readings. So if we look at our comparison between lamp and LED and the different factors that we looked at, such as lamp life, environmental factors, peak irradiance, the spectrum, heat, compatibility with adhesives, we see that there's definitely some advantages to using LEDs, such as lamp life, environmental friendly. But lamp also has its advantages in things like spectrum, and also such as adhesive compatibility. There's definitely benefits to still using a lamp-based system. If heat is a critical issue, then there's certainly benefits to using an LED-based system. And again, things like radiometry, it's a much more established technology with lamps versus LED, so there's certain benefits there. So when the question becomes which is best suited for your particular application, the answer is that it really depends upon your specific testing and your application requirements, and do the testing and confirm that the results are the same. And thanks very much. Is there any questions? All right, thank you very much.